All right, well, welcome to the second week of 337. We're going to do some applied statistics. So welcome. Fewer people here on Monday than there were last week, which is good. Right? A little more social distancing, so it's good to see you all here. Okay, so I'm going to start with a COVID update because, as I mentioned last week, I'm a stats guy. I like the numbers, I like the charts and the graphs, and I like to know what's going on, and I interpret the world better with numbers. And that's what this class is about. It's applied statistics. So let's interpret the world with numbers. So in this first slide, this is actually a bar chart that I showed you last week. And it's depicting how many cases, new cases, have occurred in the previous week. So from 8/9 to 8/16, you can tell from just looking at the height of the bar that it's just under 40. And for some reason, the number is whited out, but it's a 38. So there were 38 cases in the week prior, ending on Sunday night, the week prior to school starting. So what has happened since then? Well, the most recent update is August 21st, which is Wednesday. And since this ended on Sunday, this is really like Saturday through Tuesday of last week. And so on the 17th, 9, then 3, then 3, and then 29 on the 20th, which was Tuesday. So it's a total of 44. So as we're making these comparisons, we can see that the entire week prior, there were 38, but in 4 days, we added 44 as students came back to campus. So this is important because I want to tell you that on Monday, you were in class with at least one person who has now tested positive for COVID and could have been exposed on Monday. So that's why we're wearing the masks, and we're trying to protect each other. We don't know, when or who or how. So again, thank you for wearing the mask, for wearing them properly, because I don't want to get it, don't want you to get it, don't want to pass it along. I know that you are at very low risk. One of the people that I spoke to who had it has said, there wasn't, the symptoms weren't that bad. It was like the flu, and said it was not too bad. And that, I believe, you have the benefit of youth, maybe other benefits that we not fully understand yet, but it's probably not going to affect you very much. I'm a little bit older than you are, so my risk is a little higher, but not as high as it would be if I was 70 or older. But the thing is, my parents are 70 and older, and so is my wife's mom is in her 80s, and she doesn't drive, so we take her places. And so even if it was, I didn't spread that to someone else, and no one else got it from me, the fact that I would need to be in quarantine for 2 weeks means that there's a lot of people who would be affected, if it affected me. So I thank you for the care that you take in wearing the mask and minimizing the risk as best we can. But this got me to thinking, because as I said, stats nerd, love the graphs, love the charting, and I have actually been keeping track of the use of graphics in depicting COVID since its inception. So for instance, I would see something on television and think, oh, that's cool, and I would snap a picture of it. And so I have some graphs going really back to the beginning. So I want to show you something, and it'll kind of take you back, really. So this is from March. 64,000 cases and 897 fatalities. Remember back then? Wasn't that long ago. Now, my point is really this. I want to show you how COVID has been depicted graphically. So this is really about the stats. And I'm going to kind of critique the use of statistics in this depiction. And you'll notice most of this is from March. So I'm just kind of, I want to stay out of politics. I want to stay out of, I just want to focus on the stats. And as you look at this depiction, what stands out to you? Anything that you like or don't like about it? There should be one big glaring error, sir.
I feel like the red and the orange are like the exact same color.
How do you distinguish between the red and the orange? Awful. So there is so little distinction between those two that it makes it impossible. It's just really the same color all muddied together. So now we lose some clarity with that. Anything about the, go ahead.
New York just managed to get like 3 times more than
Okay.
the topmost state aside from.
So there's some things, some states that stand out. First of all, we see New York at 30,800 cases. So that one stands out immediately. Another state that stands out to me is West Virginia, being a yellow, which would be 1 to 99 cases, in the midst of all of that red and orange. So let's watch West Virginia as I go through subsequent slides. Let's see what happens. We see that big yellow space up in the mountain states, so Montana and Wyoming and North and South Dakota and Nebraska, all of that area. So it looks like fewer cases up there. So think about what you're learning from this depiction. And as I go through, let's see how they are getting better at depicting. Now this is another, I don't know, week or so later. So actually this will be March 27th. Okay. Look at the legend that shows you what the colors mean. What is the size, the bandwidth for each of those categories? 1 to 99, so we'll just call that 100. What's the next one? 100 to 999. So that, we've gone from a category of size 100 to a category of size 1,000. Our third category is 9,000 cases, and then it jumps from 10,000 just up to 30. 30,000 plus. So what we can see with this is the banding of these categories is pretty sloppy. Another thing you'll notice about this is every state gets one color. It's the number of cases in that state. But if you're in Springfield, Missouri, what's your risk? You can tell practically nothing about you or your particular place in the world from a map like this. So we have, again, bad color choices. Just remember, there are some people who are colorblind, so red and orange and green tend to muddy up themselves. And the reason that's important is because there's a temptation when we're talking about something where we want to lend a sense of urgency. Like red is bad, and green is good. And so we might create some kind of map that runs from red to green, and people who are colorblind, that's just going to all wash out in the mud. We won't be able to tell a difference. So actually using monochrome colors, like a darker to lighter shades of blue, it's actually more effective in depicting that data. This would be April 11. Okay, so what do you notice about the colors? Okay, we're better now. And let me go look at the bandings again. Okay, so first of all, what's happened with the size of our bands? The smallest is 1,000. Right? And what have they done with the color scheme now? Can you see how just rearranging that color scheme has gone a long way toward improving the legibility? So now the lighter colors mean fewer, darker colors mean more. It's still within that red spectrum, which is actually kind of going to go into more of a monochrome. I still don't like it as far as a depiction, but the colors are telling us more now. Now we still see New York eclipsing everyone else at 173,000 cases. And again, this is April 11. And West Virginia still seems like this little outpost of nothing's happening in West Virginia, so it tends to stay lower. But maybe there's something about West Virginia, particularly the topography of West Virginia, that might help to explain that. And now we're going to start to see better depictions that give us clearer and more useful data. So the first thing that they did was go to using dots. So rather than coloring each state according to how many cases, we'll just put a dot on that state to indicate roughly how many cases. Now this is a little bit better. There's some downsides to it. In fact, as you look at this, what is your critique of it? What is better and what is still lacking in a depiction like this?
I mean, out of the numbers, I still like seeing like how many like rough cases there was. Just seeing those dots doesn't really tell you how many people it actually is.
So the dots give you a hint,
Yeah.
but they don't really tell you how many people there are, so we don't have numbers attached to them. What does the location of the dot tell you? So you can see that what they've done is just put the dot right in the middle of the state. You know, if you just draw a square around that state, it's just geographically right in the middle. Okay. So it tells you one state relative to another, the risk or the number of cases in Missouri is going to be less than those in Colorado. And of course, New York, big dot. The dot in New York is so big now it's kind of obscuring other states. So it looks like it's kind of contained within one space, which we know that it was. It was not in upstate New York at this point. It was all around Manhattan, on the city. Although the dot itself is in upstate New York because that's where it has to fit. So again, there's some improvements here, but we can do much better. Look at what happens when we go to this graph. Okay, so now we're seeing, still using the dots, but now for the first time we're starting to see, you can tell something about yourself. So can you find Springfield on this map? Okay, you can roughly see where we are, a little larger. Now my wife works at a hospital, and so I've gotten some inside information. A lot of the cases in Springfield were not necessarily from Springfield, but outlying areas. So if you got sick in Bodark, right, you ended up in Springfield. So that's going to increase the number of cases reported in Greene County, whether or not the amount of transmission in Greene County has itself changed. So you can see which parts of the states are more affected than others. And you can see that because what is now true about those circles that wasn't in the previous? So what we've done with the circle is we've created the stroke, the line around the circle, and put a light fill in it that you can see through. So when there are multiple circles kind of stacking up around each other, we get the sense of where those cases are, and we can see through. So what we're seeing now with these dots is greater clarity because you can see the information that's underneath those. Anything else that you like about how this is being depicted now? We're definitely seeing by the confluence of dots where there are more cases. So you get information not only from the size of the dot, but how many of the dots are kind of stacked up around each other. So how do you think that they're choosing to place these dots now? You can't see it, but the choice is being made. And you could see this if we zoomed in on Missouri, we just extracted it, pulled it out, you would see that, oh, the dots are actually just in the center of each county. So what we have is county level data, and the dot, it's still in the center, but rather than one dot in the center of a state, it's one dot in the center of each county, so when you back out of that, you can now see those overlapping dots, and we can see where the cases are occurring much more clearly. What have they done here? Given up on using the diameter of the circle to convey information, and instead it's the number of dots commensurate with the number of cases. To me, does this look like something that's been left in the refrigerator for too long? There's kind of that growth of mold sort of feel to this. So it's a little more organic. It's kind of getting more visceral now. It's like you can kind of feel like there's something kind of icky about that depiction. So it's becoming a better display of data. You're not just conveying information, you're conveying information in a way that people can really grasp and react to. And so now when you start looking at, oh, where are we? You see it's not just our county. We start seeing these trends, these patterns, these subtext within the display of the dots. And we start seeing where it's happening. And if you know some of the stories of where the outbreaks have been occurring, well, you see that very clearly. So this kind of map is giving us much higher quality information. Now, all of these have been map-based. Another way that we can depict this kinds of data is using something called a heat map. Now, what you see here is that monochrome. So these are These are blue-green colors. And so we're not trying to depict, as in the last one, the red equaling danger. Here we're just interested in, give me the data, like where are the cases greatest? To do something like this, we would use the program R. And this one we could do with just R, but if you want it to be more interactive, we would use an application or a program that's installed in R, called a package. It's called Shiny, S-H-I-N-Y. Now, another way that we can depict information is through numbers. The numbers give us more information, more data. So these numbers give me the ability to make comparisons in a way that I can't with just the circles. So I can see things with these data. I can look at from Saturday to Sunday, it increased roughly 350 cases, and I can see the rate of increase, and I can get some numbers to work with. Things to look out for when you see numbers like this, if they're all ending in zeros, most of these are, they're probably a little less trustworthy. The specificity of the numbers versus the roundingness of the numbers gives you a hint as to whether or not these numbers are solid versus it's approximately 1,800. So if you see a lot of zeros, you tend to think these numbers are rounded. Let me digress and say I'm going to complain about the textbook and some things you're going to see next week as we get into doing t-testing. And that is, they go into great detail about calculating the degrees of freedom for this t-test. If you don't know what degrees of freedom are, I'll explain that in all the videos. But it's just a way we use to make some approximations of where we're going to set a cutoff point. So degrees of freedom kind of help us in establishing where we're going to say this difference is too much versus not enough, and whether we accept or reject the null hypothesis. And the textbook goes into such exquisite detail that it's going to take your degrees of freedom out to 2 decimal places. And it makes it feel like we are being so specific about these degrees of freedom. But here's the thing. Degrees of freedom are always whole numbers. They're always integers. Right? So there's no like 13.3 degrees of freedom. We just round it down to 13. And my complaint is that when we start using math to lend some specificity where it really doesn't fit, we're trying to say that statistics is this exact science, where ultimately what we're doing with statistics is probabilistic thinking. It has to do with likelihoods of things occurring. So when we get into doing t-testing next week, there will be some videos. I want you to see them because I want you to know how they're done, but we're not going to dwell on them. There will be some videos that will show you how to do really precise degrees of freedom calculations. You can safely ignore all that. That does not matter. Degrees of freedom can just be calculated in whole numbers, and if you get it wrong, if you're off by 1 or 2 or 3 degrees of freedom, it really is not going to matter in terms of your probability, which will shade by thousandths of a degree of probability. So going back to numbers, always distrust round numbers. These numbers are probably more approximate than they are precise. But this is a better way of displaying more data. So what we like about the numbers is their clarity and their specificity, but you can't have 2 weeks worth of data with all of those numbers stacking up. It's going to get too much to see. And that's where we switch over from just depicting numbers to using things like bar charts. So here we have the days, but we also have the bars that indicate the number of, these are the number of cases. And what we're seeing is a pattern. So at this point, what we're starting to see emerge is it doesn't really matter the precise number. It is that trend going up? Is it leveling off? Is it going down? We start looking for the patterns in the data. So a lot of data depiction is, what do you want to show? What is the most important takeaway? And so we will trade specificity for a larger view of the data. That's what we're doing here with a bar chart. Another way you can do bar charts is this is called a stacked bar chart. What we're doing here is we're taking multiple cities, New York, Seattle, LA, Chicago, New Orleans, and we're taking all of their cases and we're putting them all into one bar. So now what we're getting is the longer the bar, the more cases, but within that you can get a sense for how many cases are occurring within each city. The things that are most important here are, first of all, the overall length, which just gives us a sense for the change in the data. And then we're probably going to focus on what city. New York, it's the biggest slice of this bar. So what we're seeing is how are the cases in New York City changing compared to other places. And in this case, we're seeing that those rates all seem to be staying roughly the same. It's all growing at the same rate. Now, if all of a sudden New York City were to begin to shrink and Seattle were to begin to expand, the comparison between those bars is going to tell us something. It's like, uh-oh, something's happening in this city and this one's getting better or improving. Or maybe they both start to expand and that the outbreak in those two places explains the overall length of the bar. And let me show you one that's not COVID related. This is from The Last Dance about the Chicago Bulls. Here's another stacked bar chart. And here they're using 2 bits of data. One is in red, the number of titles won by each of these players, not just in the NBA, but there's an NFL player, Tom Brady. So the number of titles compared to the number of years in which they did not get a title. So we're saying, who was the best of all time? How do we answer that question? So it's basically in this graph, the longest red combined with the smallest gray gives you an estimator of who was the best, who went the most years getting a title and the fewest years not getting a title. So what I want you to see from this is that there are multiple ways of using, in this case, a stacked bar chart. So any of the statistics that we're going to learn about, there's multiple ways of using them depending on how you want to display them. So we're going to be using simpler examples, 2 different groups. We're going to measure something about each group. We're going to do some bar charts on that. What I want you to see is you're not limited just to the techniques that I'm originally going to teach you. I'm going to give you a hint at some of the other things that we can depict with good graphing as well. Now here's one. Now I'm going to complain a little bit. Bad graphing. So these is a depiction of 3 countries on the coronavirus cases worldwide. We have Italy, United States, and China. And let's look at those numbers. 80.5, 81.9, obviously I'm moving decimal place here, and then 81.7. What's wrong with this bar chart depiction, sir?
It looks like we have double of Italy's.
So it looks like the United States has double the cases from Italy. Now, what is the difference between the number of cases in Italy? We'll call it 80.5, and in the United States, we'll call it 82. Okay, so we've got a difference of 1,500 cases roughly. So the gap between Italy and the United States, this much of the bar is 1,500 cases, and the rest of the bar is 80,000 cases. Do you see why that's wrong? Now what is happening is not anchoring the y-axis at 0. Here is how this looks. I made this one up myself. Here's what it looks like when you do it honestly. And what you see is those differences evaporate, and now there's really no story to tell. It's like Italy, United States, China, exactly the same. The differences that appear in a bar chart when you're not displaying the data accurately, but disappear when you do. So it's important that we also know the difference between good or honest graphing and we be able to spot something that's not displaying the data honestly. This is an example of doing it right. So here we're getting multiple levels of information. So what do we see across the x-axis? We're seeing dates there, right? On the y-axis, not the axis itself, but the numbers above the bars, we're seeing number of cases. And then the bars themselves show us the shape of the data. So now we're getting into multiple bits of information that are being displayed. This is a much better depiction than some of the other bar charts that we've seen. Because we're seeing time frames, and we're seeing patterns, and we have actual numbers. So this is a much, much better depiction. What happens if you don't anchor the x-axis? Well, and sometimes that's less important, except when it comes to like time frames. So in this example, they're depicting time frames. That's what's moving along the x-axis. So we're going from March 1 to March 8 to March 15 to March 22nd. And then we're seeing these spikes or these colored lines that are representing number of cases. But they're starting depending on where the data begin. So what's happening, or we see, you can barely see it. If you look along the very bottom, you see Wuhan, China, which is just skating along the zero. Lombardy, which of course is Italy, we see a slow decline. What's the big one? Detroit, that's that big spike. But these are all happening at different times, and so it makes it harder to compare. Now this isn't dishonest, they made the choice to display the data this way, but if I want to do better comparisons, then I would want to anchor the x-axis, and here's what that would look like. This is, the starting point is, your 0 point is, it's not really 0, it's 100, days since 100th case. Now this, you've probably seen these graphs before. What this is telling you is the speed, the rapidity with which the cases are spreading. So now we are making fair comparisons. No matter when it came to your shores, the rate of increase can be compared. So we see the lower area, Hong Kong, Singapore, Japan, we see a flatter curve, flatter line. And then US, China, Spain, Italy, Iran, that's where we're seeing a steeper curve. So now we can compare relatively who's handling it better. So from a common 0 point, which is actually 100, I'm just calling it that's our starting point. From a common starting point, we can see the rates and we can do some comparisons much more cleanly. Is there any one of these graphs that tell you everything you need to know in a single graph? No. So it's important that we know, first it's important that we think about what do we want to show with our data, and then secondly, what's the best graph for displaying that? Greene County. So here's what's happened. Here, they're starting with when was the first case? It was March 12th, first COVID-19 case in Greene County. And now we're looking at that trend line to see how long before it doubles, or how long before we add another 100 cases. So it takes 63 days to add your first 100 cases, 32 days, so roughly half of that, to add your second 100 cases, 16 days, again roughly half, to add 300 cases, or add the next 100, I should say, to get up to 300. So what you're seeing now is that the difference between those vertical lines, that's telling you how fast the cases are spreading. Yet another way of depicting the data. Now, could we take this and start with any other county and put these two graphs together? If it's graphed in the same way, we could see. So we could say, if we have a county that puts into place a masking ordinance, what happens to the span between those vertical lines? Does it increase, decrease? Does it change at all? We can do fair comparisons that way. So if we wanted to answer a question like, does having a masking ordinance work to decrease the number of cases? This is the kind of graph that we can make honest comparisons with. I want to get into something you heard early on. We haven't heard it for a long time. Flattening the curve. Remember that? Okay. Flattening the curve was referring to essentially what I was showing you here. So how long does it take for that curve to increase? So the curve obviously comes from that exponential increase. If there's more gap between those vertical lines, your curve is flatter, and if there's less gap between those vertical lines, your curve is steeper. So flattening the curve is just a way of saying expanding the time for the adding or the doubling of cases. Trying to keep that flatter. And here is what that looks like in the public health literature. We're going to talk a lot about things like normal curves and distributions. And what I want you to see with this is, or what I want you to take away from this is, the area under each of these curves is the same. What I'm saying is it's 100% under each curve. So what we're looking at is how we're spreading out or increasing or decreasing really the variability or how close those cases are to one another. So the idea of flattening the curve is let's spread it out over more time so that the number of cases doesn't overwhelm the hospital facilities. But what I want you to take away from this is we're going to talk a lot about curves and distributions, and the difference between, let's say, the darker curve versus the striped curve is the amount of variability. There's much more variability in that lower, flatter, it's called called platykurtic, a more platykurtic, flatter curve. Much more variability than there would be in the leptokurtic or taller curve. Now here's one more. This is bar charts. But the bar charts are single lines, and when you pack them all together, you get the distribution. Except here, it's not 100% under the curve. Here is more like truly a bar chart where higher curves mean more. And I love looking at charts like this because I can think about what was happening in 2002 or 2006 or 2012 and watch these little trends. So this is jobless rate. So it's seasonally adjusted applications for unemployment. The reason it's seasonally adjusted is, we're close to Branson, so there are people who work all summer during the tourist season into the fall, and then when the tourists go home and the weather gets cold, they go on unemployment until the spring, and then they're back at it next year. It's just kind of like part of the economic reality for them. So we want to adjust for that. We want to smooth out those spikes. And you can see, obviously, the 2008 recession, we see that big spike. We start to see that slowly declining. We can watch that change over years. And the reason I show you this is for the context. Because when we back out a little bit further, that's what 3 million looks like compared to that trend over time. So when you hear numbers, big numbers, 3 million, 2 million, we lose track, our human minds lose track of what those millions look like. So a depiction like this gives us the context in which to make those kinds of comparisons. So all of that was about the display of data. I thought it was just a good explanation for the big picture of what we're doing with statistics. And it's also something that I just particularly enjoy. I like doing graphs and charting. And I like spotting ones that are done poorly and saying, I know what's wrong with that graph. I'm going to teach you those kinds of things as we go along. So now I'm going to bring it back down to what was our real point for this week, which is talking about the statistics software. Before this class, has anyone heard of JASP? One person. Anybody? Two. Okay. So why have you not heard of JASP? It's relatively new. It's not as well known as a program like SPSS or R, RStudio, Stata, some of the more even Excel, some of the more common packages for doing statistics. So why am I telling you about it? Because JASP strikes that sweet spot between ease of use and power. Now, all of the statistics that we are going to learn about, we can do in Excel. And that's the whole point of the textbook. How to do these statistics in Excel. If you've read ahead at all or skimmed it or just looked through it, you probably might have felt a little overwhelmed. I have felt overwhelmed looking at this, looking at how they're showing you to do particular tests in Excel, and I think, oh man, that's way too hard. We could do that so much easier. Now we could do it easier in SPSS, it's just that SPSS costs a lot of money, and you could get your own copy for this semester, but after this semester you wouldn't have it again unless you paid for it or got a subscription, and then, that's no good. And I could teach you in R. This is an example of R code. This is for a t-test. This is a simple t-test. And this is actually the same data as what you'll be using next week when we do this first example. What I want you to see from this is, if you're new to t-tests and you're trying to get your mind wrapped around what we're doing in statistics, and then I give you this code, I just feel like it can be overwhelming. I struggle to write this code, and I've been doing this for years, and I still make mistakes, and it's so frustrating when you do something and you think you have it right, and then you run it and it doesn't work. And it's like, who do I ask? And you've got to go either search online, or maybe you know someone who knows how to use R and you seek their opinion. It can get frustrating. The reason I'm showing you JASP is it is powerful, it's legit, you can use it just like you would R, you can rely on these results. So this is a solid program to use, and you are going to find it so much easier to use. And you'll see that as we get into doing t-tests next week. Before we wrap up, any questions? All right, thank you so much for being here, and I will see you guys, see you guys next Monday, and I'll see the other group on Wednesday. So take care, thanks.